So for 2 videos now, we have talked about electron configuration, and I know you are probably tired of hearing it, but it's electron configuration, and that's just part of the game that we have to play in general chemistry and organic chemistry, but just a little bit in organic chemistry, not much. Okay, so I want to go back and I want to talk a little bit about electron configuration just for a second, and I'm going to kind of work through a full example with you. And this example is going to be the electron configuration for sodium. So if I ask you to do the electron configuration for sodium, you are going to write down 1s2, 2s2. Here, let me draw that a little bit better because that's a scribble and a chicken scratch. Like my handwriting's not bad enough as it is. 2s2, 2p6, and then 3s1. There is the electron configuration for sodium. And we said if we wanted to show all of the principles, blah, 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 then we can do that by drawing the boxes down here below. So S only has one option, so both of those have to go in with opposite spins. S only has one option, both of those have to go in with opposite spins. P, those come to us in 3 different degenerates, px, py, pz, so I draw 3 boxes. There's 6 electrons there, so I start filling them in, and I do one at a time in the boxes. 1, 2, 3, I run out of room. I go back to the first one, 4, 5, and 6. Again, I draw the barbs in opposite direction because they have opposite spins. And then finally, 3s. Well, S only has one option, and there's only one electron that's there, and that's all alone. Poor thing. Don't you feel sorry for it? So there's the electron configuration, and there's the electron configuration showing all of the principles that we've talked about up to this point. In the textbook, you're probably going to see a diagram that looks like this. And this is exactly what we're doing here. So there is no difference. I'm just telling you to draw boxes around this thing. And this diagram actually draws the arrows with 2 barbs, a full arrow that points up and a full arrow that points down. Whichever way you want to do it, I don't really care. As long as you show them in opposite directions, that's really all that matters. So, 2 barbs, 1 barb, you pick your pleasure, and that's the way that you'll do it from that point on. In addition to this, just to recap, nitrogen has atomic number 7, so therefore it should have 7 total electrons, right? Count the number of arrows. 1, 2, 3, 4, 5, 6, 7. There you go. Here we have 1s2, here we have 2s2, and here we have 2p3. And that p is broken down into 3 degenerate orbitals. And there is a box on the first one, a box on the second one, and a box on the third one. All right, so there's px, py, pz. Now, this is not where it stops, folks. I wish it was, but this is not really where it stops. Because back in a previous video, I kind of told you that sometimes these electrons in the outside shell get a little happy. And when they get a little happy, I said at that point, they kind of get a sugar rush and they become uncontrollable. And they become so excited that, boop, out they go. Okay, well, if that's the case, then this atom loses a negative charge. Okay, it was neutral. The number of positives equaled the number of negatives. But if we get a chance to form an ion, and that was the term that we used, I briefly introduced it, then that ion could do something funny with the electron, either lose it or gain it, and we get a charge that is on this atom. Okay, well, why am I bringing that up? Well, let's say that we have nitrogen. And let's say that we have nitrogen minus 3. Well, that's an ion. There's a charge here. Doesn't matter if it's positive or negative, it's a charge. So it's an ion. In particular, this thing is called an anion. And think of the N that represents the word negative. Well, on the opposite side of this, we could have something like sodium and Na+. Well, this is also an ion. We call this a cation. And think of the T for positive. All right, so anions and cations are all out there. They will come around with the elements that we use on a daily basis. And they help drive chemistry as well. So we have to talk about them. Well, the problem here is that they begin to change the whole concept of what we've discussed in the past 3 or 4 videos now at this point. So what if I was told to get the proton number, the electron number, and the neutron number of nitrogen and of N-3? How do we do that? Well, my advice to you is always start with the normal first, okay? So if I go back to this periodic chart and I look at nitrogen, right here we are, that is atomic number 7. Okay, so automatically I know that we have 7 protons, 7 electrons, and if I go back, I'll look at 14 as the mass number, so 14 minus 7, it just so happens to be 7 again. So there's 7 down the row. 7 protons, 7 electrons, 7 neutrons. Well, notice what I said. I didn't say anything about protons doing anything, right? I didn't say anything about neutrons doing anything. What I said is that electrons can be lost and electrons can be gained. So when we get an ion, like N-3, the proton number stays the same. It has to. This is the identifier. 7 protons, that means we've got nitrogen, folks. It's nitrogen. It could be a charged nitrogen, but it's at least nitrogen. The neutron number will also stay the same. There's no difference there either when it concerns ions. The only thing that changes is the electron number. That's it. So that electron number tells me that this nitrogen has 3 extra negatives. That's why it's a negative charge. Okay, it's like having a bank account. You have a bank account with $0 in it. You spend $3. You went into the hole. $3. Okay, well, electrons are kind of the same way. That was a transaction that you made. That transaction rolled in an extra 3 that you spent. Well, what was 7? You add 3 to it. And that gives me a total of 10. That is how we handle proton, electron, and neutron number when it concerns these charged atoms. Okay, well, what about valence electron count? All right, well, if I go to the periodic table and I look at nitrogen, nitrogen right up here at the very top has 5 valence electrons, right? So 5 valence electrons the normal nitrogen had with it. Folks, this is one of the reasons that it gained the 3 in the first place, because I mentioned this concept of octet. And this octet, the magic number was 8. How many does nitrogen need in order to get to 8? 3 more. So what this nitrogen has decided to do is to go through and scour the environment for 3 extra electrons, and it found them. That will bring its total. What was 5? You added 3 extra. So that does get added to that valence count. And now we have 8 valence in the outside shell. That's where they get added. So if this nitrogen atom added 3 electrons to its orbitals, its subshells, where do they go? They go to the outside layer. And that outside layer, by definition, is the valence electron count. So it does change that value as well. Okay? Now let's do the same thing with sodium. We have protons, electrons, neutrons, and I'll go ahead and do valence count here at the very bottom. All right, so we'll draw this, and I'll make this nice little pretty table. If I go to the periodic table, I find sodium. Sodium's right here to the left at number 11. Okay, so I automatically know that sodium, normal sodium, has 11 protons and 11 electrons, just by looking at that number. If I want the neutron number, well, this was 22.98. Let's take 22.98. Let's round that to 23. I'd be okay with that. It's so close. And I'm going to take 23 minus 11. And this gives me a total of 12. So I'm going to say 12 neutrons. That's fine. If we're not perfect, so what? It's not what I'm after here. And valence number. Well, this sodium up here at the very top is in group number 1, 1A right there. So that valence electron is a 1. Now, what if we had to do it with the cation side? I told you always start with the original. It seems to be the easiest. Well, proton number is not going to change. All right, neutron number is not going to change. The only thing that changes are the electrons. The electrons are leaving, the electrons are gaining. And in this case, we have lost an electron. It was neutral, 0. It loses an electron. It loses a negative charge. Therefore, it now becomes positive for that reason. If it loses a negative, it's now positive. So if we lose an electron, what was 11 is now going to be 10. And what was 1 will now be 0. However, it's actually 8. Why? We'll see that a little bit later. Remember, octet rule. Octet is where it's at. So this is the way that we would handle a anion or a cation when it concerns charges and when it concerns the proton, electron, neutron, and valence electron count of those atoms. Well, folks, electron configuration is also affected. So nitrogen and nitrogen minus 3. In nitrogen's case, if I go back here, and let's write the electron configuration down here at the bottom. I'll start up at the top, 1s2, 2s2, and then I go to 2p, and nitrogen's the third one over. This is regular nitrogen. This is what we've always done up until this point. But what if we had a -3 charge on that nitrogen? That means that this nitrogen gained 3 electrons, gained 3 more than what it had before. All right, well, if it does, 1s2, 2s2, 2p, it did have 3. It's gained 3 more. So 3 plus 3 is now 6. We call that 1s2, 2s2, 2p6. This fulfills the octet for it. So it changes the electron configuration too because there's extra electrons that we have to represent. Sodium, it would be the same way. Let me go ahead and draw that one. Normal sodium, 1s2, 2s2, 2p6, 3s1. Sodium plus, well, it received the plus because it lost an electron. If it loses an electron, then what happens is that I take that outside electron and I get rid of it. There's nothing there. And this is 3s1. That 3s1 disappears. Poof! Away it goes. Now, I keep telling you, octet, octet, octet. How is it that when they lose 1, they get 8? Folks, look at your outside valence shell now at this point. You have just eliminated that third onion layer. You are now back to the second onion layer. There's a 2 and there's a 2. Add these up. There's a 6 and there's 2 more in spherical shape, and 6 plus 2 is 8. There's 8 valence electrons now in the outside shell because we've eliminated that outermost shell that it had to begin with. We got rid of that 1 electron. It was easier to get rid of that 1 electron to get to this 8 number than it was to gain 7 more. It's all about the valence shell. It's all about the outermost layer. It really does help stabilize the atom in a way as far as the electrons go. So that is how you handle charged atoms if they come around. Now there's going to be one more term, and this term is called isoelectric. Isoelectric basically refers to this concept that when we get charged atoms, they change their electron configuration. And if they change their electron configuration, as in the case of N-3, then this configuration could match another one. So let's say that we didn't know this was N-3, and I just gave you this electron configuration, and I said, what atom is this? 1s2. Okay, there's 1s. There's 2. 2s2, lithium and beryllium. 2p6. There's P, there's 2. So boron, carbon, nitrogen, oxygen, fluorine, neon. You would say, hey, this is neon's electronic configuration. And that's true. It is. But it's also N-3's electron configuration as well. Because we have now went a little bit haywire with the charged species. So for that reason, these are called isoelectronic. They have the same electronic configuration as each other. One is normal neon, and the other one is N-3. Sodium plus, this is not its normal electron configuration, right? This is a charged atom. It changed the electron configuration for that reason. So what is it isoelectronic to, or isoelectric to? Well, 1s2, 2s2, 2p6. What would that be? Well, there's 1s2, hydrogen, helium, 2s2, lithium, beryllium, and 2p6, boron, carbon, nitrogen, oxygen, fluorine, neon. Neon, again, is isoelectronic with Na+. So all three of these folks are isoelectric with each other. The Na+ has the same electron configuration as the N-3, and that has the same electron configuration, those do, to neon. That's why these are kind of called noble gases. These are the celebrities of the periodic chart. Everybody on the chart would love to be a noble gas. Everyone wants to be that celebrity profile. And the reason is because they got bank. They got a lot of money. They're famous, right? People like that. Well, these elements like it too, but in their case, money is a octet. All of these noble gases have octets. They all have 8 electrons in the outer layer of their shells. And all of these other atoms would love to replicate what they are doing. And that is why you see nitrogen maybe form N-3s, because this is a way that it could copycat some of those noble gases on the periodic chart. Sodium could become Na+, and it does that willingly because it allows it to get the octet, which is like a celebrity on the chart, and that's like the noble gases that we have. So this is the whole reason that we get these charged atoms. This is why it happens. This is why not everything stays nice and neat and neutral the entire time. That's just the way that it is. So this is the way that we handle charged atoms. And those will be questions that you're going to see on an exam or an online quiz or some type of an assignment. You're going to see them give you examples of neutral atoms, and you're going to see them give you example of charged ones. And this is how we handle them. Look at that charge, look at what's written up here in the top right-hand corner, and that will tell you what it's doing. If it's negative, you have gained those electrons. There's more of them now at this point. If they're positive, then you've lost that many. So if there was a positive 3, you have lost 3 electrons. If this was a -2, you've gained 2 electrons to give it a -2 charge. All right, so with that said, I think that temporarily we are done with electron configuration and proton-electron count for now. So in the next video, we'll continue on with general chemistry review, and we'll bring out some new definitions. And those new definitions, hopefully, is not going to be a new thing for you. It will be a review, and if so, you've had a good teacher. So congratulations, you picked the right person to take Gen Chem with. So we'll get back to it when you watch the next video. Stay tuned.